So this next part we'll discuss about RAS, namely reliability, accessibility, and serviceability. For us to sell into a customer, the performance is kind of the entry point. They're going to test the performance, and if they need such performance, they will want to move forward. But what's really going to be the main challenge for them to test and confirm is how reliable is this solution, and can it really last in their data center and in high duty cycle? And to that end, we as the solution provider, as a software provider, need to be able to deal with any kind of conceivable failure of any kind of part and anything that can happen in this pretty complex topology. More than that, the hardware we use is really bleeding edge, kind of raw hardware. So we can't tell the customer, oh, look, we got you a very new SSD from that guy, so what do you want? They have firmware problems. We need to own it. And we are implementing here features in RAS that we've only implemented at IBM maybe 4 years after GA. But that's a level of maturity that we need to exemplify. And when we talk to customers, we had this bug a year ago where we didn't recognize properly that a switch was completely shut down. So the customer says, oh, I had Pure Storage here yesterday. They didn't have that problem. That's what we're being sized up against. Nobody cares that we're a startup. They expect tier 1 availability and tier 1 reliability, and there are no excuses around it. So we put a lot of effort into many different features. So guided repair actions, graphical indications, and SNMP traps on any kind of alert and any kind of fault. We monitor everything in the SSDs, in the network cards, in the enclosures. We manage all the firmwares, the BIOS, the IPMI, the fans. We monitor fan rate. Who does that? We need to do it because if a fan failed, something very bad might happen down the road. We report the system alerts through emails or through SNMP. We, of course, support network multipathing. That is not a feature. It's like what would be the good example? There is no such thing that the network will not fail at some point. People upgrade the network gear or they disconnect the cable by mistake. Not having network multipathing is a non-starter. We support concurrent upgrade. That's a very complex and difficult feature. So we need to upgrade both the software on the controllers and the software on the agents. We have support for that, which is fully automated and concurrent. We have power protection. We have thermal shutdown. We've had cases where the power was on at the customer's data center, but the air conditioning was off. Mm-hmm. Do you know what that does to the equipment? It cooks it. So we need to do a thermal shutdown. To do a thermal shutdown, you need to monitor thermal sensors. It's not enough to say sensor 7 thinks it's too hot. Maybe it is too hot for sensor 7. It's a complex feature. We have call home. We have reverse SSH support to debug systems in a secure manner. We've done all of those things because we've been schooled by the best at IBM that those things are really important. And by the way, we have a demo of our RAS and our GUI on our YouTube channel. So a bit about our RAS architecture, and the way we've structured it is basically a 3 kind of layer handling a few different things. Layer 0 is also known as hardware abstraction layer, abstracts over the enclosure and the SSDs that we use. There are variants and minute differences and sometimes huge differences between enclosures and SSDs. So to be able to write software once, we provide a hardware abstraction layer over those SSDs. So true, NVMe is a standard, and enclosures are just x86 servers, but you'll be surprised or terrified if you saw how different the SSD vendors interpret the NVMe standard. Now, we don't impact NVMe or SSD vendor implementations. When we talk to the vendors, they always ask us, oh, what kind of feature would you guys want? We don't want any feature. We want to use off-the-shelf hardware. We want to be as generic as possible. We have qualified every dual-port NVMe SSD known to man, and we will continue to do so. And by now, all the major vendors have dual-port NVMe SSDs. but the variances are large, and that's why we need an abstraction layer on top of it. The next layer is the network abstraction layer, which is what allows us to deal with different networks, different network topologies, different NICs, different switches. Again, there is a myriad of options of how you build your network, whether you use layer 3 RoCE, which is routable, or layer 2 RoCE, which is encapsulated over Ethernet, whether you use that kind of RoCE lossless feature or RoCE lossy feature. And of course, this is where also supporting NVMe over Fabric comes into play. Finally, the layer on top of that, abstracted over the network and abstracted over the hardware, is where we do the data services, and that's where we also do the host driver. To drive into a little more detail, the kind of functions that each layer contains, just to give an example, enclosure management, so it's power, fans, thermal, IPMI and BMC, how you manage enclosures. These are very basic things. Redfish and Swordfish are the new standards for how to manage data center equipment. And firmwares. If you don't know what firmware you have on the system, it's not clear what's going to happen. SSD management, so we have basic RAS, both in-band and out-of-band. By that I mean out-of-band is like a hard error, like the SSD goes down. In-band is within I/O information, like a soft or a hard medium error. All kinds of log pages and alerts that they export, or their temperatures, and again, the firmwares. In network management, basic things, you need to set up IP addresses on the box. You may need to set up VLAN. You may need to set up network quality of service, like traffic classes and priorities. There's various RoCE options that you may or may not use. Things that relate to the topology. Some people have a single switch topology. Some people use 2 for high availability. Some do a lift and spine design. Some do a 3-tier hierarchy. It creates all sorts of noise down the line at our end and then at the other end. When you do NVMe over Fabric, the target, you need to identify the LANs and the namespaces from the SSDs to the NVMe over Fabric. There's things like the registration and authorization at that level of protocol. And finally, in layer 2, so our host driver has got to hook itself up to VMs potentially. Maybe you want to map our volume only to a single VM or to a single container. And of course, in bare metal deployments. And the data services like RAID, high availability, replication, multipathing. And finally, our kind of homebrew NVMe over Fabric initiator, which is basically a distributed all-flash array. So this is what allows us to use quite easily different SSDs without modifying too much, or different enclosures without modifying too much, or different networks without modifying too much. We just need to plug in the module for new SSD from vendor A into this level. And we've been able to pick up Optane SSDs with very little effort. And we actually have a live POC, as Andy mentioned, using dual-port Optane SSDs.
So do you see a market for lots of different enclosure sizes? I know you do 2 already. But you said, I think, when we chatted, that one was much more popular than the other.
So we chose to focus on the TU24 because it's kind of ubiquitous form factor. It's dense plenty. We see enclosures coming with like 1 petabyte in 1U. Mm-hmm. It's a bit hard to see who will put 500 grand on a 1U box and a single failure domain. But there's not a lot of effort for us to support that kind of box. So right now, the TU24 seems to carry most use cases. I don't think anybody told us it's not dense enough. There's also power considerations. 24 SSDs driven to the max is about 700 watts. If you start doubling the number, you get into problems. So a lot of the vendors with very dense enclosures, they throttle them down and hurt the performance again. But again, we're software. We can adapt pretty much to any enclosure. Our dual-port NVMe enclosure has been first to market, and as far as we can tell, it's still the only one that's off the shelf that anybody can order. It's not our design, and we have nothing on it. We just order it from AAC, a Taiwanese ODM that we work with. And anybody can order it from them. So the E8 agent is very interesting. It's mostly implemented in user space, and it does have a thin kernel shim driver. So the green part in this chart is the stuff that is part of the system, unmodified, and these two things are ours. So customer applications run unmodified, and they talk to the block device Linux stack, which is part of kernel. We need a kernel shim driver in order to be able to intercept the block device kernel stack in Linux. There's no way to do it without the kernel shim driver. But we've elected to implement the entire logic and the entire agent service in user space. And for various reasons, we're following here what many other similar companies did, which is to avoid writing kernel code as much as you can, because it's more complex, it's much harder to debug, both in the lab, but particularly in the field. The cost of a kernel error to the customer is tremendous. The cost to a user space bug is very, very small. In fact, our user service can crash and restart itself almost immediately without causing any impact, and we get a log of what happened in case that happens.
Does that give you an issue with context switching between kernel and user mode? Or is it...
There is context switching here, and the cost of that, including our RAID 6, is about 10 microseconds overhead on our data path.
Okay.
But we don't think you can build resilient storage otherwise. The kernel also, there is the whole licensing issue that lurks with it. It is really a bad approach. The kernel shim driver acts, it's basically got three interfaces. One, it hooks to the block device. The other, it talks to the service. And the third, it shoots down things to the network. So when Bill did the demo, he created a new LUN. And immediately, you saw a new block device on the host that was connected to E8. That's because we're running the agent there. And it represents to the block device stack a new device. And the block device stack doesn't know that it looks like a local SSD, whereas in fact, it is a remote and virtual SSD. But that means that you don't need to modify anything on that station. Whatever applications you use, whatever local file systems you use, whatever you used to do before, you can continue to do it happily, and we're not asking you to modify anything.
Okay, where's that 10 microseconds exit is that time to when you pass the packet to the RNIC, or is that the total?
We just measured the difference from if you use an NVMe drive here.
Okay.
Instead of this.
So that's the total overhead.
Yeah. When we measure...
Including transit.
When we measure latency, and it's odd that some vendors don't do it this way, but the way to measure latency is from here. You run FIO and see what it says. Or you run the customer application and see what it says. Breaking down latency in between is interesting, difficult to do, highly variable. But at the end of the day, this is where we measure latency from.
Well, I guess it's interesting, but it points to the future that you might need to optimize in certain areas in the future. So knowing it internally for your own purposes, obviously, has benefit.
It's true, and I think our roadmap is rich with such improvements and optimizations. One last slide. People often ask how much effort do we take on customer servers. So a single core running the E8 can do about 100 to 200,000 IOPS, including RAID 6. If you use RAID 0, you get much higher numbers. Assigning multiple cores on the same server gets you higher IOPS in a linear fashion, or assigning more cores on different servers will get you higher IOPS, again, in a linear fashion. That's the horizontal scaling. So you could have 128 servers running one core, or 64 servers running 2 cores, or 16 servers running 8 cores. You get roughly the same performance in all cases.
You don't need QoS because you just pick how many IOPS do I need, how many cores do I put, boom.
You sometimes need network QoS if you're competing on the converged Ethernet with the general purpose traffic.
On the network side, yes.
Yeah. And that is something we have spent a lot of energy on to be able to manage and track that you can run general purpose traffic and EA traffic on one network. That is the huge value prop of 100 gig Ethernet. So when Julie compared 100 gig Ethernet to 32 gig fiber channel, I think the questions people need to ask themselves, if I have 100 gig Ethernet anyway in the top of the rack switch, what the hell do I need 32 gig fiber channel for now?
Well, especially you don't need.
So that I don't have to share the switch with the network guys.
Well, yeah, there is that.
There is that. In the future, offloading to smart NICs will reduce this footprint. So this is certainly something that's very interesting.
So it's only going to get faster.
It will only get faster. And the premise of E8 is to be able to be forward compatible and future compatible with even faster SSDs. Optane is a great example of that. E8 was designed to unleash the bottleneck, and it is forward compatible to new SSDs, and adopting Optane has been very simple. That was my last slide, so thank you everyone for your patience and learning about E8 storage. It was a great opportunity for us to present. There's any other questions?
Dare I ask how much?
I think that's a fair question. I think that's a fair question. Definitely ask it.
Yeah.
What's the licensing model? How much is
How much? And suppose I want not a fully loaded box. Let's go entry level. What's the smallest box I can buy into, and a price range?
So there's entry level on the 2, on the 1U. We should achieve cost parity with today's all-flash arrays and give you something between 10 times to 40 times their performance.
Okay, so on a cost per gig base, well, gig terabyte, I guess we should be saying now.
As a startup, we need to be 10 times better than the incumbents, which we are. And we cannot cost more because people will just buy from them.
Yeah.
So that pretty much sets the constraints.
So we generally say we are generally between $2 and $3 a gig.
Okay. And you guys are doing that without tons and tons of data reduction code and all the rest of it.
Correct.
You're getting $2 or $3 a gig off the shelf.
It is the actual cost of the box, and we're not playing any funny
Silly
data efficiency games with the
games,
calculations now.
projections. Yeah. Okay, that's very attractive.